In our next step, we draw some inspiration from Theorem 10, which is saying that when your operator A on a Hilbert space X is positive definite, and your projections Pn not only strongly converge to the identity, but are orthogonal projections, then this combination Pn is always applicable to A. Okay, with that theorem in mind, you could come across the following idea. If someone gives you the good old problem to solve the equation ax equals b for a given right-hand side b in some space y, and the given operator a from x to y, not necessarily positive definite, x and y could be different, but at least x should be a Hilbert space and a should be invertible. Then, by theorem 10, you could get the following idea. Take your equation ax equals b and multiply it by a star. Then, of course, you get the following equality that you often call the normal equation of the original equation. And you do that especially when the original equation is not solvable. We will do that quite often in the next chapter, chapter 4. But in our case, this equation is solvable because A is invertible. And because A is invertible, also A star is invertible. The inverse of A star is just the inverse of A and then star. And that's why you can also go in the other direction here. So this is an equivalence. But now you get this new system that has the same solutions as the old system because they are equivalent. But the new system is in some sense nicer because the system operator or matrix is now A star A instead of A. And A star A is always positive definite. And you can check that via the definition. So you have to show that this scalar product of A star A times a vector x with the same vector x is always positive. But of course you can get A star here over across the comma to the other side, where it becomes A star star, which is just A. But then this scalar product of ax with itself is just the norm of ax squared. And because A is invertible, A is in particular injective, so ax is only 0 when x is 0. So in all cases where x is not 0, this is not the 0 vector, so this gives you a positive answer. So indeed, yes, the matrix is positive definite, or the operator. But this means that our simple trick here transforms this pretty usual system ax equals b into one of those great systems with a positive definite operator to which our theorem 10 applies. So that theorem 10 says that we can solve our new system and hence our original system approximately by solving the projected equations, where you take your equation here and simply put pn's to both sides of the operator and in front of the right hand side. And the only assumption on your sequence Pn is that they are orthogonal projections that converge strongly to the identity. So what a great idea. We can take an arbitrary system here, transform it a little bit, and then get a system to which the finite section method applies. We have a proof. Well, why am I not more excited, or where is the problem? And the answer is numerics. Exactly. So this is one of these moments where you hate numerics because you have this idea, then you have your proof, and you get your solution, and then comes numerics. So what exactly do they have to moan about? Their first point of criticism is that the new system matrix is expensive to compute. And their second point of criticism is that the condition number squares when you pass from the operator A to the operator A star A. We will talk about condition numbers in the next chapter, and that will be next week or maybe the week after that. Just briefly, the condition number tells you how sensitive the solution of your system is to perturbations, so to errors of the right-hand side of your system. So the condition number is computed purely based on the matrix. And if your condition number is 10, then that means 1% error in your right-hand side might result to 10% error in your solution, which is not great. But if you square that, then 10 becomes 100, and well, then you don't want to do that computation anymore. We will see that we cannot argue with this point of criticism, but we will work on this. And by the way, in the end, it will turn out that somehow you can even avoid the complication too. Okay, so how do we do that?